Good day everyone, welcome to Cryptonomus. Today we will be discussing the future of GPU acceleration in data centers. The demand for graphics processing units, or GPUs, in data centers is experiencing an unprecedented surge. These powerful chips are no longer just for gaming or graphics. They have become the workhorses of modern computation, especially for complex tasks. Data centers around the world are rapidly adopting GPU acceleration to cope with the massive amounts of data being generated daily. This trend reflects a fundamental shift in how we process information. The need for faster, more efficient computation is driving this transformation forward at a remarkable pace, reshaping the digital landscape. Market growth projections for data center GPUs are truly astonishing. The sector is expanding at a phenomenal rate. In 2024, the market was valued at approximately $18 billion. However, forecasts indicate a climb to an incredible $183 billion by the year 2034. This represents a compound annual growth rate of around 14.2%. Some analysts even predict the broader data center market, heavily influenced by extreme parallel computing and AI, could reach a staggering $1.7 trillion by 2035. This highlights the immense economic impact and strategic importance of GPU technology in the coming decade. NVIDIA currently holds a dominant position in this burgeoning market. Their influence is hard to overstate. In 2023, NVIDIA commanded an estimated 98% share of the data center GPU market. This translated to shipping around 3.76 million units. Their revenue from this segment alone reached approximately $36.2 billion. This dominance is built on years of innovation and a strong software ecosystem. While competition is emerging, NVIDIA's early lead and continued advancements like their Blackwell architecture for PCs launched in January 2025 solidify their current standing as the primary enabler of GPU acceleration. The initial and still primary drivers for this GPU adoption are artificial intelligence, or AI, and high-performance computing, or HPC. AI applications, particularly machine learning and deep learning, require the parallel processing capabilities that GPUs excel at. Similarly, HPC tasks in scientific research, weather forecasting, and complex simulations benefit immensely from GPU power. These fields demand computational speeds far beyond what traditional CPUs can offer efficiently. As AI models grow more complex and HPC tackles ever larger problems, the reliance on GPUs will only intensify, further fueling their integration into data centers globally. Beyond foundational AI and HPC, a diverse set of catalysts is fueling the GPU acceleration boom. Generative AI, including large language models, or LLMs, has exploded in popularity and capability. These models demonstrate the raw power of accelerated computing, requiring vast GPU resources for training and inference. Big data analytics also benefits immensely, allowing businesses to process and extract insights from enormous datasets faster than ever before. Furthermore, the global expansion of 5G networks is creating more data and enabling new applications. For instance, 5G subscriptions in regions like India are expected to reach 970 million by 2030, creating a fertile ground for GPU-powered services. A fundamental technological shift is occurring within data centers. We are witnessing an accelerated transition from relying primarily on x86 central processing units, or CPUs, to adopting GPUs and other specialized accelerators. This change is driven by the nature of modern workloads, especially AI. These tasks demand massive concurrency, performing many calculations simultaneously, which is a core strength of GPU architecture. While CPUs are excellent for general-purpose tasks, they cannot match the parallel processing efficiency of GPUs for these specialized, intensive computations. This shift is not just a trend, it is a necessary evolution for continued progress. This technological evolution brings significant changes to data center infrastructure itself. Facilities are growing larger and consuming far more power, with some new builds reaching 200 megawatts. Average power densities per rack have more than doubled to 17 kilowatts and could hit 30 kilowatts by 2027. Such intense power requirements necessitate new designs in mechanical and electrical systems. Advanced liquid cooling technologies, including direct-to-chip cooling and liquid immersion, are becoming essential to manage the heat generated by dense GPU deployments. These systems can also improve energy efficiency, a critical concern for sustainable operations. To unlock the full potential of these powerful GPUs, supporting infrastructure must also advance. High-performance storage solutions, such as NVMe solid-state drives or SSDs and all-flash arrays, are crucial for feeding data to GPUs rapidly. Slow storage can create bottlenecks, wasting valuable GPU processing time. Equally important is ultra-high bandwidth, low-latency networking. Technologies like InfiniBand and high-performance Ethernet are vital for connecting multiple GPUs and servers, enabling them to work together seamlessly on large, distributed tasks. The entire data center ecosystem must evolve in concert to support this new era of accelerated computing. While NVIDIA is the current leader, the competitive landscape for data center GPUs is dynamic and evolving. Advanced Micro Devices, or AMD, is a key challenger, offering its Radeon Instinct series of GPUs. AMD introduced new chip designs across its portfolio in November 2024, signaling its intent to capture more market share. Intel, a giant in the CPU world, is also making significant inroads with its Xe graphics architecture and the acquisition of Habana Labs, which specializes in AI processors. These established players are investing heavily to compete, bringing more choice and innovation to the market, which ultimately benefits consumers and industry progress. Beyond these major semiconductor companies, other significant players are shaping the market. Broadcom, for example, is strong in data center infrastructure, providing critical intellectual property for custom ASICs, or application-specific integrated circuits and networking components. They have robust relationships with major cloud providers like Google, for whom they supply components for tensor processing units, or TPUs, and Meta, for AI chips and networking solutions. Amazon Web Services, or AWS, is also developing its own custom silicon, such as Trainium and Inferentia chips. These offer cost-optimized alternatives for AI workloads within its vast cloud ecosystem, presenting another facet of competition. Emerging companies are also entering the fray, often with highly specialized AI architectures. Firms like Cerebras, Sambanova, and Graphcore are introducing novel approaches designed specifically for AI tasks. While they offer impressive performance for certain applications, they often face challenges with software compatibility and building a broad ecosystem comparable to NVIDIA's CUDA platform. Nevertheless, their innovation pushes the boundaries of what is possible and keeps the pressure on established players. The inference segment of the market, focused on running trained AI models, was dominant in 2024, holding a 56.5% share, indicating a strong demand for deploying AI applications at scale. Regionally, North America, particularly the United States, held a dominant market position in 2024. It captured over 37.1% of the market share, with revenues around $6.6 billion. This dominance is fueled by government initiatives promoting energy-efficient GPUs, a strong focus on data security, and the presence of leading tech companies. The US data center GPU market alone was valued at $5.4 billion in 2024. However, the Asia-Pacific region presents significant growth opportunities. Rapid technological adoption and substantial investment in digital infrastructure across countries in this region are set to drive massive demand for GPU acceleration in the coming years. Europe is also focusing on energy-efficient computing solutions. The business benefits of adopting GPU acceleration in data centers are compelling and multifaceted. Firstly, it leads to enhanced workflow efficiency. Tasks that previously took days or weeks on CPUs can often be completed in hours or even minutes with GPUs, significantly reducing bottlenecks. This speed allows businesses to iterate faster and bring innovations to market more quickly. Secondly, GPU acceleration can lead to cost savings. While individual GPUs can be expensive, their efficiency means fewer servers might be needed overall, optimizing hardware usage and reducing associated operational costs such as power and cooling for a given workload. Furthermore, GPU-accelerated data centers provide the crucial ability to handle ever-increasing workloads without requiring constant, disruptive infrastructure overhauls. This scalability is vital in an era of exponential data growth and escalating computational demands from AI and big data applications. Businesses can adapt more readily to changing needs, ensuring they remain competitive. The on-premise deployment segment held a significant 56.4% market share in 2024, indicating many organizations still prefer direct control over their accelerated infrastructure. Though cloud service providers, capturing 48.9% of the market, are major drivers of AI-ready data center demand. Despite the immense potential, several challenges and risks could impact the trajectory of GPU acceleration. Supply chain fragility is a significant concern. The manufacturing of advanced GPUs relies heavily on a few key players like TSMC, and any disruptions, whether geopolitical or logistical, can affect availability and prices. The high implementation costs, encompassing not just the GPUs but also the necessary power infrastructure, advanced cooling systems, and skilled technical support, can be a substantial barrier, particularly for small and medium-sized enterprises, or SMEs. These factors require careful strategic planning. Other potential headwinds include the risk of an AI winter or an economic downturn, which could dampen the current enthusiasm and reduce infrastructure spending. The dominance of NVIDIA's software stack, CUDA, while a strength, could also be challenged by the rise of robust open-source alternatives, potentially leveling the playing field. Regulatory pressures concerning AI ethics, data privacy, or energy consumption could also impact deployment strategies. In the longer term, emerging technologies like quantum computing and optical computing, or even ultra-low-cost specialized AI chips, could disrupt the current GPU dominance, though their widespread commercial viability is still some years away. Edge computing and the rise of AI PCs are also trends to watch, distributing processing power. For more details on this and other topics, go to www.cryptonomus.com. You can also follow us on Facebook, Twitter, Instagram, and LinkedIn, and subscribe to our YouTube channel at Cryptonomus. Thank you.